Okay, so I've been thinking about the basic block diagram. I've been working it out. I drew it out because I drew a previous block diagram, and then I did a bit more thinking about it, and that's when I added the MOSFET switch to um, the output. So what we basically have is we use a flip-flop, which is a flip-flop IC, which is triggered by an NE555 timer to flip it, so that when the flip-flop is active, we need to use at least two outputs. One output would be to trigger the solid state relay bank 1. The solid state relay bank, let me just find somewhere to point because it's hard to do. Oh, my blooming drawing's falling off the right. So it's hard to explain this really. So only one of these solid state relay banks is active at a time, because the way I explained it previously was that each solid state relay, it consists of 8 channels. I think it's 8 channels. Anyway, we're using let's see, let me just work this out because I've forgotten something. 1, 2, 3, 4, 5, 6, 7. We're using 7 channels actually. Yeah, so that's right, 8 channels. Right, so when solid state relay 1 is active, it's connecting one battery array as series, which is the high output, which is why I put high there, and it's configuring the other battery array as parallel, so that these batteries are in parallel. And the output, remember this is a block diagram, it's not actually a circuit diagram. So when this battery is configured as parallel, it's obviously low because it's low voltage, right? And the logic circuit would go through the comparator, which monitors the voltage on each bank to determine when that voltage is dropping below a certain threshold point. When the voltage of the series battery bank drops below a certain threshold point, it will trigger the NE555 timer, which would send a pulse to the flip-flop, which would then activate to reverse the arrangement, so that the other batteries would then be switched over, so that it will be switched so that the battery that was previously low will become high, and the battery that was previously high will become low, right? So the voltage would then go through a bridge rectifier, and the bridge rectifier is full wave, so it's 4 diodes, and then it would run through the MOSFET switch, which is also intermittent because it's only set on to conduct power out, while at the same time the solid state relay is active. So if that solid state relay is activated, then the then the MOSFET switch will be active. And in between, when none of them are active, because there's a crossover point, a dead time if you like, so when the other solid state relay just before it becomes active, the MOSFET switch will be re-energized, solid state relay energized at the same time, so it will now conduct. Because the problem with these solid state relays, as I explained previously, is they're designed for AC. And normally on the crossover point, when the AC waveform is changing from a positive cycle to a negative cycle, they normally disengage automatically. But because we're using DC, they have a tendency to stay latched. and that is the problem I've been trying to avoid. We want to make sure that the solid state relays do not continue to conduct when they're disengaged by the flip-flop. So when they flip-flop disengage a solid state relay, we want to make sure that the power is no longer conducted through the batteries. Otherwise, if the other solid state relay is active, we have a dead short, and then we have fireworks basically, and that's not good. So anyway, this is my basic block diagram. Obviously, I tried to simplify it as much as I could, because obviously I could have connections or logic connections coming from the battery all the way down to the bridge rectifier and everything else, but I tried to keep it simple so that it doesn't get too jargoned and cluttered up. And obviously the MOSFET switch out sends the output voltage to whatever load we're running, and some of the voltage obviously from whatever, if we're running a generator or a dynamo, well, a generator anyway, we could send power back from the generator to whichever battery array is set to the high, you know, which is the output. So we can send some of that power back, hopefully to supplement any losses or overcome any losses that we might have due to thermal and all that stuff, you know. So that's the idea anyway. I did think about sending the power back to the batteries that are in parallel, but the problem with that is we would impede the efficiency of the circuit in the fact that the high side is what's powering everything. So it's better to send that power to the high side, because the high side is by its nature sending wattage through the load into the low side anyway. So it makes sense to send that voltage back to the high side. So whichever battery is connected in series, we would try to supplement any losses by sending that energy back to the high side, because it's pointless sending it to the low side, because all you're going to do is detract from the output of the high side, because as the low side starts to increase in voltage, the actual high side has a bigger voltage drop across on the low side. So we actually subtract energy efficiency from by doing it that way. So it makes more sense to actually send power to the high side, because by doing that we're actually charging the low side at the same time. If we go back to that circuit, that what if I did this drew, so this is the diagram from the Tesla diagram, where there's the LED there. What we would have is a bridge rectifier, full wave bridge rectifier, and then it would go through a MOSFET switch. So we'd have a full wave bridge rectifier there and a MOSFET switch. So no matter which way around these batteries were configured, whether these were in series at this side, these are in parallel, or these were in series and these in parallel, whichever way around they are, the bridge rectifier would still send a DC output, and we wouldn't have to use two MOSFETs. We'd only need to use one MOSFET, because it would be on the other side of the bridge rectifier. So that's basically what I've come up with so far. As I say, I'll get to it. I'll get to building it on the breadboard. As soon as my eyesight's starting to get a bit better now because of this infection and my eye infection. My eyesight seems to be improving a little bit, but things are going to get better once you get rid of this damn sofa. So I'm getting a leather chair, which will hopefully negate problems, because I've got some kind of allergy with that sofa anyway. I don't know what's going on with that, but yeah. Anyway, that's me working out the logic diagram for the moment. So anyway, that's it for now. Hope it helps.